In the summer of 1958, a 24-year-old graduate student at the University of Chicago received a classified assignment from the United States Air Force. His name was Carl Sagan. Not yet a professor, not yet a television host, a doctoral candidate in astronomy who had never held a security clearance in his life. His task was to calculate what would happen if a nuclear bomb detonated on the surface of the moon. Not as a thought experiment, not as an academic exercise, as an operational plan funded by the Pentagon with a code name, a timeline, and a budget. Sagan was asked to model the behavior of a nuclear dust cloud expanding in 1/6 gravity and near vacuum conditions. The project had been running for weeks before he joined. At least 7 other scientists were already involved. The study would produce 8 classified reports in 8 months, and the question it aimed to answer was breathtaking in its audacity. Could the United States intimidate the Soviet Union by detonating a nuclear weapon on the moon, visible to the naked eye from Earth? 8 months earlier, on October 4, 1957, the Soviet Union launched Sputnik, a polished aluminum sphere roughly the size of a beach ball circling the Earth every 96 minutes. Americans could hear its radio signal on shortwave receivers. They could see it crossing the night sky, a pinpoint of light moving among the stars. The psychological impact was devastating. If the Soviets could put an object in orbit, they could put a warhead anywhere on Earth. The technology was identical. That single beeping satellite shattered the assumption that American technology was superior. Within weeks, the American public demanded answers. Congress held emergency hearings. Newspaper editorials questioned whether the United States was falling behind in science, in engineering, in national security. President Eisenhower tried to reassure the public, but the damage was done. The Soviets followed Sputnik with Sputnik 2, carrying a dog named Laika into orbit. America's first satellite attempt, Vanguard TV-3, exploded on the launch pad on live television. Newspapers called it Flopnik, Kaputnik. The humiliation was total. Leonard Reiffel was a 31-year-old physicist at the Armour Research Foundation in Chicago, later known as the IIT Research Institute. He was brilliant, methodical, and accustomed to classified work. In the spring of 1958, the Air Force Special Weapons Center approached him with an unusual request. They wanted a feasibility study. Could a nuclear detonation on the moon serve as a visible demonstration of American military capability? Reiffel assembled a small team. The project received a dry, bureaucratic designation, a study of lunar research flights. Its internal code name was Project A119. The Air Force needed something the entire world could see. Not a weapons test in the Pacific, not a missile launch from a classified range. Something no telescope could miss and no government could deny. The moon was the perfect canvas, 240,000 miles away, visible from every nation on Earth. A nuclear flash on its surface would be the ultimate demonstration of reach. If the United States could strike the moon, it could strike anywhere. That was the message. According to records from the period, the Air Force wanted the detonation visible to the naked eye. The plan called for detonating the weapon near the terminator, the sharp boundary between the sunlit and shadowed sides of the moon. This was not an arbitrary choice. A flash on the bright lunar surface would be washed out by reflected sunlight, but near the terminator, a burst of light would stand out against the darkness of the shadowed terrain. The dust cloud, kicked upward by the blast, would rise into sunlight and glow, visible from Earth. Reports suggest the weapon under consideration was a small device, likely in the range of 1 to 2 kilotons, roughly a tenth the yield of the Hiroshima bomb. Gerard Kuiper, one of the most respected planetary scientists in the world, served as a consultant on A119. He had mapped the lunar surface, studied its composition, and understood its geology better than almost anyone alive. Kuiper recommended a young doctoral student for the team, Carl Sagan. At 24, Sagan was already developing a reputation for thinking across disciplines, combining physics, chemistry, and astronomy. He was eager, ambitious, and willing to take on classified work without asking too many questions. His assignment was narrow but critical. Sagan's specific task was to model the expansion of a nuclear dust cloud on the Moon. On Earth, a nuclear blast produces a mushroom cloud because hot gases rise through the atmosphere, pulling debris upward in a distinctive column. The Moon has no atmosphere, 1/6 the gravity. The physics would be entirely different. The dust would expand outward in all directions, a spherical shell of pulverized rock and vaporized soil. Without air resistance, particles would travel farther and faster. Sagan had to calculate how high the cloud would rise, how quickly it would disperse, and critically, whether it would be luminous enough to see from Earth. Between May 1958 and January 1959, Reiffel's team produced 8 classified reports. Each one addressed a different aspect of the feasibility question: delivery method, weapon selection, blast effects on the lunar surface, visibility from Earth, potential contamination of the lunar environment, scientific value, if any, of the resulting data. According to Reiffel's later accounts, the team was thorough and professional. They approached the question the way engineers approach any design problem, systematically, without moral commentary built into the analysis. One of the key concerns was radioactive contamination. A nuclear detonation on the Moon would scatter radioactive material across the lunar surface. In 1958, no one knew whether humans would ever walk on the Moon. But the scientific community was already discussing lunar exploration as a serious possibility. Contaminating the Moon with radioactive debris could compromise future scientific missions. Instruments designed to study pristine lunar soil would instead measure weapons residue. The Moon, untouched for 4 billion years, would carry a permanent American scar. For Reiffel, this was not a minor footnote. It was a fundamental objection. Consider what the detonation would have looked like. A rocket launched from a classified military site, arcing through space for roughly 2.5 days. Impact on the lunar surface at the edge of shadow. A blinding flash lasting perhaps a second. Then a cloud of dust and debris rising slowly into sunlight, catching it as it expanded into a pale, luminous sphere. No sound. No shockwave propagating through air. Just light and motion in absolute silence. From Earth, observers with telescopes would see a brief bright point, then a faint expanding glow. The naked eye might catch the flash itself, depending on atmospheric conditions. The Soviet Union had its own plan. Known as Project A119, it was developed by a team of Soviet weapons scientists exploring the same question from the other side of the Iron Curtain. Could a nuclear detonation on the Moon demonstrate Soviet technological supremacy? The parallels were remarkable. Both superpowers independently reached the same desperate conclusion: that the Cold War's psychological battlefield had expanded beyond Earth. According to accounts that emerged after the fall of the Soviet Union, the A119 team conducted their own feasibility studies. The Soviet team reportedly canceled Project A119 for a reason that bordered on the absurd. Their scientists concluded that the nuclear flash on the Moon might not photograph well enough from Earth. The explosion, while theoretically visible, might not produce images dramatic enough for propaganda purposes. A faint dot of light on a distant surface, viewed through Earth's turbulent atmosphere, might fail to impress. The greatest nuclear demonstration in history, and the Soviets worried it would look underwhelming on the evening news. The irony is staggering. Both superpowers independently decided to nuke the Moon, and one canceled because the explosion wouldn't be photogenic enough. While the Soviets worried about photographs, the Americans faced a different calculus. Reiffel himself was among the first to raise the alarm. By late 1958, scientists advising the Air Force began to argue that the public relations disaster would be catastrophic. The United States was trying to position itself as the leader of the free world, a force for peace and scientific progress. Detonating a nuclear weapon on the Moon, visible to every human on Earth, would undermine that narrative completely. Allied nations would be horrified. Neutral nations would be alienated. For Reiffel, the man running the study, this was becoming personal. Sagan's calculations revealed something unsettling. The finest particles, micron-sized grains of vaporized rock, would reach escape velocity and leave the moon entirely, drifting into cislunar space as a faint radioactive cloud. The coarser material would rain back down over several kilometers. But the critical finding was about visibility. Without atmosphere to shape a mushroom cloud, the visual effect would be fundamentally different from any nuclear test humans had ever witnessed. More subtle, more alien. For a 24-year-old writing his first classified report, the conclusion was stark. The spectacle the Air Force wanted might not be the spectacle they would get. If the detonation had occurred, the crater would have been modest. A 1 to 2 kiloton device would carve a depression roughly 20 to 40 meters across in the lunar regolith. From Earth, even the most powerful telescopes of the era could not have resolved a crater that small. The permanent scar would be invisible to observers. But as Reiffel's team had warned, the radioactive contamination would be real, spread across several kilometers by the debris field. Any future mission landing nearby would encounter elevated radiation. Somewhere in a Chicago lab, the project lead was already drafting his recommendation against proceeding. Getting a nuclear weapon to the moon in 1958 was itself an enormous technical challenge. The Atlas missile, America's first operational intercontinental ballistic missile, had only begun flight testing that year. It could barely reach orbit, let alone achieve the velocity needed for a lunar trajectory. The Air Force would have needed a dedicated launch vehicle, purpose-built for this mission. Reports suggest planners considered modifications to existing rocket designs, but the engineering was marginal at best. Reiffel's team knew the math. The United States could not yet reliably reach the moon with a spacecraft, but it was planning to reach it with a bomb. In January 1959, Reiffel submitted the final report. The study concluded that the detonation was technically feasible, but strategically inadvisable. The visibility from Earth was uncertain. The contamination risk was real. The international backlash would be severe, and the scientific community would never forgive the military for destroying pristine lunar terrain. Reiffel recommended against proceeding. The Air Force accepted his conclusion. Project A119 was shelved. No announcement was made. No press conference. The reports were sealed, classified, and filed away. For Reiffel, it was over. For Sagan, the complications were just beginning. Carl Sagan applied for a prestigious Miller Fellowship at the University of California, Berkeley. The application required listing publications and research experience. Sagan, eager to demonstrate the breadth of his work, referenced his involvement in a classified study of the lunar environment. He did not name Project A119 directly, but he provided enough detail that anyone with knowledge of the program could identify it. Reiffel later described this as a significant breach. In the world of classified research, even hinting at the existence of a program is a violation. Sagan had effectively told Berkeley that he had done secret weapons work for the Air Force. Classification rules in the late 1950s were unforgiving. Unauthorized disclosure of classified information could result in criminal prosecution, loss of security clearance, and permanent exclusion from government research. For a young scientist building a career, these consequences would be devastating. Sagan had not leaked technical details. He had not shared calculations or conclusions. But he had acknowledged the existence of a classified program, and in the intelligence community, that alone was a serious violation. According to Reiffel, the breach was noted internally. However, the Air Force appears to have decided that pursuing the matter would draw more attention to A119 than the leak itself. So the Air Force stayed silent. Sagan's career continued. He received the Miller Fellowship. He went on to Berkeley, then Cornell, then Harvard. His trajectory was unbroken. But the classified work from that summer in Chicago never appeared on his official curriculum vitae. It existed in a gap, a period of research that produced no publications, no citations, no public acknowledgement. For decades, only a handful of people knew what the young astronomer had spent those months calculating. Sagan himself rarely spoke of it. The work was walled off from the public persona he was building. By 1959, the political winds had shifted. The initial panic over Sputnik was giving way to a more focused response. The National Aeronautics and Space Administration, NASA, had been established in July 1958. The Mercury program was selecting its first astronauts. The question was no longer how to intimidate the Soviets with a nuclear flash. It was how to reach the moon with human beings. The same fear that had driven A119, the desperate need to demonstrate American capability, was being channeled into something extraordinary. And Carl Sagan, the young man who had modeled nuclear dust clouds, was watching this transformation from Berkeley, carrying a secret he could never mention. On May 25, 1961, President John F. Kennedy stood before a joint session of Congress and declared that the United States would land a man on the moon before the end of the decade. The resources that might have been spent on nuclear demonstrations were redirected to Apollo. Billions of dollars, hundreds of thousands of engineers, scientists, and technicians. The moon became a symbol of peaceful achievement, not military dominance. Kennedy's speech did not mention Project A119. No one in that chamber, save perhaps a few Air Force officials, knew that just 2 years earlier, the Pentagon had considered a very different kind of lunar mission. On July 20, 1969, Neil Armstrong and Buzz Aldrin walked on the lunar surface. The soil beneath their boots was undisturbed. No radiation, no crater from an American warhead, no contamination from a Soviet bomb. The moon was exactly as it had been for 4 billion years. The decision to shelve A119, made quietly in a Pentagon office a decade earlier, had preserved the most important scientific site in the solar system. Armstrong's footprints would have landed in a very different landscape if Reiffel's recommendation had been overruled. Carl Sagan never spoke publicly about Project A119 during his lifetime. He went on to become the most recognized science communicator of his generation. Cosmos, broadcast in 1980, reached hundreds of millions of viewers in 60 countries. He championed nuclear disarmament, space exploration, and scientific literacy. The man who had once calculated nuclear explosions on the moon spent his career arguing against the weaponization of space. Whether that early classified work shaped his later activism, no one can say with certainty. But the trajectory is striking. From weapons physicist to peace advocate, all starting in a Chicago research lab in the summer of 1958. Leonard Reiffel kept the secret for over 40 years. He watched Sagan become famous. He watched the Apollo mission succeed. He watched the Cold War end. And he said nothing about the summer of 1958. It was only in the year 2000, 4 years after Sagan's death, that Reiffel broke his silence. He published a brief account in the journal Nature, confirming for the first time that Project A119 had existed. He named Sagan as a member of the team. He described the study's conclusions. The response was immediate. The media was stunned. When Reiffel's account was published, the reaction was a mixture of shock and dark fascination. The idea that the United States and the Soviet Union had independently considered nuking the moon struck many as a perfect distillation of Cold War madness. Historians noted that the project revealed how far institutional thinking could drift from public values when driven by fear and competition. Scientists pointed out that the decision to stop, not the decision to start, was the remarkable part. The system worked, barely. A handful of scientists argued against a plan endorsed by the Air Force, and the Air Force listened. Reiffel noted that the classified reports from Project A119 had never been found in any archive. Despite multiple searches, the 8 documents produced by his team between 1958 and 1959 appear to have been destroyed or lost. No copies have surfaced in declassified Air Force records. No copies exist at the IIT Research Institute. The physical evidence of the project has vanished. What remains is Reiffel's testimony, Sagan's oblique fellowship reference, and the institutional memory of a plan that nearly happened. The paper trail was erased. Only the human memory survived. If Project A119 had gone forward, the cascade would have been swift. The The Soviet Union would likely have accelerated its own E-4 program, detonating a second device, then a third. The lunar surface, instead of inspiring wonder, would have become another Cold War battlefield. The Outer Space Treaty of 1967, which banned nuclear weapons in space, might never have been negotiated, because the precedent would already have been set. Apollo astronauts might have landed on irradiated soil. Neil Armstrong's first words from the moon would have carried a very different weight if a nuclear scar lay just beyond the horizon. The true legacy of Project A119 is not the plan itself. It is the decision to abandon it. In a decade defined by nuclear brinkmanship, proxy wars, and ideological confrontation, a small group of scientists looked at a feasible military operation and said the cost was too high. Not the financial cost, not the technical cost, the cost to humanity's relationship with its own sky. Reiffel understood this. The moon is a shared inheritance. Contaminating it for a propaganda photograph would have been an act of vandalism against the species. The restraint shown in 1959 made the triumph of 1969 possible. But what did that restraint cost the man who calculated the blast? In the last decade of his life, Carl Sagan campaigned tirelessly against the weaponization of space. He argued against the Strategic Defense Initiative. He warned about nuclear winter. He wrote about the fragility of Earth as seen from space, a pale blue dot suspended in a sunbeam. He never publicly connected these convictions to his work on A119, but the connection seems inescapable. The 24-year-old who calculated nuclear dust clouds on the moon became the 62-year-old who pleaded with humanity to protect the cosmos from its own worst impulses. Some lessons, it seems, begin with classified arithmetic. Tonight, if you step outside and look up at the moon, you are seeing a surface that almost bore the scar of a nuclear weapon. Two superpowers independently planned to detonate a bomb upon it. The calculations were made, the reports were written, classified, and then lost. The young scientist who did the math became the man who taught the world to look at the stars with wonder instead of fear. The secret stayed buried for 4 decades, outliving the man who carried it most visibly. And the moon, 4 billion years old and counting, remains exactly as it was, untouched, unscathed. A testament to the moment someone decided that not everything should be a weapon.